Let's solve another thermodynamic problem, this one involving an ideal gas used in a particular polytropic process. Air is contained in a piston cylinder assembly, initially at 40 psi and 600 degrees R. The air expands in a polytropic process with N equal K equal 1.4 until the volume is doubled. Modeling the air as an ideal gas with constant specific heats, determine A, the final temperature in degrees R and pressure in psi, and B, the work and heat transfer, each in BTUs per pound mass of air. Let's lay out our storyboard. Our schematic shows a piston cylinder assembly filled with air. And I've drawn the boundary line around the air molecules. So the system is nothing but the air. Here's what we know from the problem statement. State 1 has a pressure of 40 psi and a temperature of 600 degrees R. State 2 has a volume that's twice the original volume. And this process, 1,2, is an expansion process with PV to the n power, and n is K. Its PV to the 1.4 power is constant. That also tells us that K is equal to 1.4. We can also note that the molecular weight of air is 28.97. Here's a PV diagram of this process. We're going to start at state 1 at 40 psi and some volume V1, we don't know what it is, and a temperature of 600 degrees R. And we're going to go through a polytropic expansion, which always shows up as a concave line, to state 2, where the volume is twice the original volume. The pressure is unknown and the temperature is unknown. And we're going to model this as a closed system, of course, with delta KE and delta PE equal to 0. We'll assume the air is an ideal gas. And in this polytropic process, N equals K equals 1.4. So it's a polytropic process with N equal to 1.4. But K, the ratio of specific heats, is also 1.4. And if we're astute at this point, we will note that whenever we have a polytropic process with N equals K, it's an adiabatic process. Adiabatic meaning that there is no heat transfer. So we'll confirm this, but right now, if we're clever, we'll figure out that this is an adiabatic process. Also, because we're given a value of K, where K is constant, and K is the ratio of specific heats, C sub P over C sub V, then specific heats can also be taken as constant. And here's what we need to find. We need to find the final temperature and the final pressure. And we want to know the work and the heat transfer in units of BTUs per pound mass. Let's start by solving for the final pressure, which we can do simply by using the polytropic expression. We know that P1 V1 to the n power is constant. Therefore, P1 V1, in this case n is 1.4, is equal to P2 V2 to the 1.4 power. So rearranging, we get P2 is P1 times V1 over V2 to the 1.4 power. We can plug in values. We know P1 is 40 psi. We have V1, and V2 is just 2 times V1, and all that raised to the 1.4 power. So now I've got P2 is 40 psi times just 1/2, the V1s cancel. We have 1/2 to the 1.4 power, and I calculate that P2 is 15.16 psi. Now, let's solve for T2 using the ideal gas law equation. We know that PV is MRT, and one of the methods that we can use for using the ideal gas law is to use it as a relationship between state 1 and state 2. Well, in this case, we look for values that are constant. Well, M is constant in a closed system, and the gas constant is by definition constant. So I'm going to set them aside by themselves and rearrange the equation to give me PV over T as MR. Now MR is constant. So now I can write P1 V1 over T1 is P2V2 over T2. And I know that V2 is 2 times V1, so I can substitute that, and then my V1s cancel. And I get P1 over T1 is simply 2 times P2 over T2. Rearranging and solving for my unknown, T2 is 2 times the ratio of P2 over P1 times T1. Let's substitute values. T2 is 2 times P2, which is 15.16 psi, divided by P1, which is 40 psi, all times the temperature at state 1, which is 600 degrees R. And I calculate that T2 is 454.8 degrees R. Let's recognize that there was another way to calculate T2. In textbooks, you'll find many relationships for an ideal gas that's involved in a polytropic process. There are quite a few of them. And there was one of particular interest to us in this case, and it simply says that T1 V1 to the K minus 1 power is constant. So we write T1 V1 to the K minus 1 power is equal to T2 V2 to the K minus 1 power. And I'm not going to work out all the details here, but basically we know K and we know everything but T2. And solving this expression, and I'll leave this to you, T2 is 454.7 degrees R. Exactly the same answer we had from using the ideal gas law. Now, let's find the work done on a unit mass basis. There's also two methods I'm going to show you to do this. Let's start with method 1. We know that work per unit mass for a polytropic process where n does not equal 1, we've solved this integral before, and we came up with P2V2 minus P1V1 over 1 minus n. And it's work divided by mass because our volume term is a specific volume. Now, the ideal gas law says that PV is RT. So we can replace these PV values in the work term with RT. So we have work per unit mass is R times T2 minus R times T1 divided by 1 minus n. I can factor out the R. And I get work per unit mass is R times T2 minus T1 over 1 minus n. Solving using our variable values, we have R is 1545 divided by the molecular weight of air of 28.97. This quotient having units of foot-pounds force per pound mass R times T2 minus T1. I have to convert foot-pounds force to BTUs, and all of this over 1 minus n. And I calculate that W over m, which we'll signify as small w, the work per unit mass is 24.9 BTUs per pound mass. Now let's solve for work another way. We recognize that when we have a polytropic process with n equal k, that the process is adiabatic. And an adiabatic process is one where the heat transfer is 0. So let's write an energy balance. For a closed system with no changes in kinetic or potential energy, we can simply say that delta U is Q minus W. Well, if Q is 0, we simply have W is minus delta U. And we can write delta U as C sub V times the mass times delta T. Let me divide both sides by m, and I get the work per unit mass, or small w, is equal to minus C sub V times the change in temperature. Well, let's calculate C sub V. C sub V is R over K minus 1, where R is 1545 divided by the molecular weight of 28.97, and that has units of foot-pounds force per pound mass R. I'm going to convert foot-pounds force to BTUs. And this is all over K minus 1, where K is 1.4. And so I calculate a value of C sub V of 0.1714 BTUs per pound mass. Now we can calculate the work. It's simply minus C sub V times delta T, where T2 is 454.7 and T1 is 600 degrees R. And I calculate that the work is 24.9 BTUs per pound mass. Let's calculate Q from an energy balance. Assuming that we didn't recognize that this process was adiabatic, we can determine that with this energy balance. Q is delta U plus W. That's our basic closed system energy balance. And I'll rewrite delta U is M times U2 minus U1. Divide both sides by the mass, and I have Q over M is U2 minus U1 plus W over M. We'll rewrite that as small q, that's the heat transfer per unit mass, is the change in specific internal energies plus the work per unit mass. But we know that U2 minus U1 is C sub V delta T when we're using constant specific heats. And we've already calculated C sub V. And so we can substitute this expression into this equation here. And we get Q is C sub V delta T plus work. Let's plug in values. We have our C sub V value from our previous work. We have T2 minus T1. And we have the work term, which we also previously calculated. It's 24.9 BTUs per pound mass. So Q ends up being this first term, which comes out to be a minus 24.9 BTUs per mass, plus our work term, which is a positive 24.9 BTUs per pound mass. It gives us a value of heat transfer of 0 BTUs per pound mass, which implies that the process is adiabatic, which if we were clever, we already noted without doing all this work.